We're winding down here, guys. We got a couple more things to cover here this year, and then we are done. Today we're going to cover what we call the gold foil experiment. Sometimes we call it the alpha scattering experiment. If you've taken chemistry, you might be somewhat familiar with this. We started off with the Dalton solid sphere model of the atom. Right? The atom is indivisible. The atom is the atom. It's the pool ball model of the atom, or the solid sphere model of the atom, or the marble model of the atom, where each of the atoms are different, but you can't break them down any further. And then we had the Thomson plum pudding model, or the raisin bun model of the atom, where the nucleus consists, or the atom consists of a sea of positive charge with a bunch of little electrons floating around inside it. The Rutherford, we call it sometimes the planetary model of the atom, was, I think, beyond an evolution of the model of the atom. I would almost call it a revolution in the model of the atom. The Thomson raisin bun model was the first to identify that there was subatomic particles, but the Rutherford model is the first one to look remotely close to our current model of the atom. It's not right, it's not perfect, but it's much, much closer to what we currently believe the model or the atom to look like. So I would consider it to be almost as revolutionary as Thomson's raisin bun model of the atom, even though it didn't establish the existence of any new types of particles, like Thomson's model of the atom did. All right, Rutherford and his assistants named Geiger and Marsden. Remember the name Geiger from anywhere before? Have you heard that before? Geiger counter, yeah. So his assistant went on to do some pretty important things as well. Rutherford and his assistants performed this experiment called the gold foil experiment, or the alpha scattering experiment, essentially where they had a box of radioactive material that generated alpha particles. It's not a box of alpha particles, it's a box of something like uranium-235 or something that produces alpha particles that get released through this hole in the box right here, and they end up being fired towards this really, really thin layer of gold foil. It's like gold leaf. Do you know what gold leaf is? Like, you can buy it in a grocery store and put it on baking for decoration and eat it, actually. It's really, really, really thin gold foil. So Rutherford and his assistants fire these alpha particles at this gold foil, and they surround the whole thing with a screen called a scintillation screen that glows when alpha particles strike it. You don't need to know that word, scintillation. It glows when these alpha particles strike it. So we're able to determine where the alpha particles strike the screen. And what they find is that the alpha particles don't strike the screen all in the same spot. They find that most of the alpha particles go straight through. So most of the alpha particles go straight through the gold foil as if the gold foil isn't even there. Some of the alpha particles, though, go through but are deflected. So instead of going straight through, they hit the gold foil like this, and they maybe deflect like this, or they maybe deflect even more like this, or they maybe deflect upwards like this. Some of the alpha particles are deflected. Now, most of them, remember, still go straight through, but some of them are deflected. It's like football field has a Canadian football field has 110 yards on it. We have 110 people, one at each yard of the football field, and we aim them directly across, and we blindfold them, and we say, one at a time, go. Most of those 110 people end up making it to the other side of the football field straight across, okay, with no issues whatsoever. But some of those 110 people, when we let them go one at a time, end up making it across the football field, but not straight across. Their path was changed by something. Make sense? A few of the alpha particles bounced back. You go to our analogy again for a second. That would be like saying a few of the people that we lined up, sent across the football field one by one, ended up making it back to the same side as they started. Not in exactly the same place necessarily, but they never made it across the football field. So let's say we have 110 people going across. 100 of those people end up going straight across. 9 of those people end up making it across, but in a different place than they started, a different yard line than they started. 1 of those people end up bouncing back and ending up somewhere nearby where they started. How could we explain that? If most of those people ended up straight across the football field, if most of the alpha particles ended up going straight through, then what do we know about the composition of the football field or the gold foil? Most of it's got to be empty. Most of the atom is empty space. Just like most of the football field, if 100 people make it across, most of the football field is empty space. There's nothing in the way. Some of the alpha particles were deflected. Well, some of the people's path on the football field were deflected. What could explain that? Yeah? Well, something's like they're coming close to something that's pushing them off their path, right? Like you're walking across the football field, something, you got a blindfold on so you don't know what it is, but something's pushing you off your path, right? Well, what's going to push a positively charged alpha particle off its path? Something that is positive. But it's got to be small, right? Because most of the atom is empty space. So this, whatever this positive thing is, has got to be small. We're going to say there is a small positive nucleus. Oh, look, it's the existence of the nucleus. We don't just have a bunch of negatives floating around in a sea of positive charge. We've got a nucleus now that is positive. Not protons and neutrons yet, but it's positive, at least. A few of the people walking across the football field bounce back. A few of the alpha particles bounce back as well. What does that tell us? Sorry? They came really close to them, or they hit something, and they bounced back. But we know something about what they hit. If we send Kira running across the football field, and she hits a little 2-year-old that's happening to be standing in a football field, what's she going to do to that 2-year-old? She's going to plow right through that poor little kid, right? And she's going to end up somewhere on the other side, right? But that doesn't happen. Kira ends up bouncing back. So what did she hit? Like a 300-pound offensive lineman or something, right? Which caused her to bounce back. So we know that this nucleus, this small positive nucleus, must also be heavy or dense. Not suggesting that football players are dense, but what Kira must have hit in the middle must have been heavy or dense. So this small positive nucleus is heavy or dense. This led Rutherford and his assistants to come up with a model of the atom that looks like this, the planetary model. There is a small, dense, positively charged nucleus. Well, the electrons that Thomson discovered have got to be somewhere. Those electrons are orbiting around in circles. Call it the planetary model of the atom because it looks an awful lot like the solar system, right? Where the planets orbit around the sun.